Hello, in this segment, I will go through the answers to the following quiz questions. They are basic assembly language and C language oriented questions. So very quickly, we will summarize the answer here. First question, match the appropriate assembly statement to the description. So we need to find out memory to register, which statement matches that. This is in the AT&T syntax. So memory references are given with a parenthesis. So it could be either this, this, or this, these three options. We need to transfer the memory to register. Therefore, we need to find out the destination is a register. Naturally, the one that I highlighted is the answer because it has a parenthesis here. Percentage EBX with the parenthesis means memory reference. EAX is a register name, so this makes sense. The rest are all not relevant for this case, as you will see soon why. Okay, so this is the first one. Immediate to memory means there's some constant that you move to a memory location. So here's a constant and you move to a memory location. Memory location, as I mentioned earlier, has a parenthesis followed by a register name. So this is the answer. Register to register means you have both source and the destination as a register, and register to memory means the destination should have a parenthesis. So it could be this or this or this, but we need to have a register. Therefore, this is the answer. And then finally, memory to memory, there is no such instruction possible. So it is NA. That's basically the answer for the first one. Let's move on to the second question. Consider the following disassembly code. Okay. The question is, how many bytes does the function add use to represent its code? So if you look at the disassembled code, you can see we start from 0 index to 24. That means there are 25 bytes. The bytes are basically 55, E9, E89, E5, E3, E7, EC10, and so on until C3. Okay. So this is 25. EDX, EAX instruction will update the EAX register. The answer is yes, because in AT&T syntax, this is the destination. The meaning of this statement is that you take whatever in EDX and put it into EAX after adding it with EAX. So it's same as saying EAX is equal to EAX plus EDX approximately. Okay. So the answer is yes. Move on to the third question. Consider the following code fragment in 32-bit architecture. So we have a C code sort as character C int I. I is not a regular int, but it's a pointer to an int. Okay. We are given some addresses, like S has the address, something that you see here. C has the address. And the question is, what is the value of ampersand S plus 1? Ampersand S means address of S. And adding 1 means not just adding 1 in a regular integer arithmetic. It means that you need to look at the data type. Since S itself is short, ampersand S means pointer to a short type. So if you add a pointer to a number, you need to look at the size of the data type. Okay, we can look at the options and easily figure out what could be the possibility. Ampersand S, okay, here is yes, right? This is the value of address of yes. And what is the meaning of adding 1? Okay, we assume here short is 2 bytes. Therefore, we need to add just 2 to it, okay, which is basically, this is hex addition. So it's 9 and then A and the B. So it must be either this or this. Okay, at this point, and ampersand C plus 1. So you basically take the character type and add 1 to it. That means it could be again this or this. Now we can rule out these two answers. And what is I plus 1? It's okay. I itself is an integer pointer type. So you're now having an address, adding 1 to it means address plus 4. We assume integer takes 4 bytes. Therefore, we need to just add 4 to whatever and I is pointing to. Okay, I is pointing to this address. So we add 4 to it. So B plus 4 means in hex addition, C, D, E, F. So the answer is something that ends with F. Assume that you're debugging using GDB in Little Indian architecture. Okay, and I is an integer. What is the value of I? Okay, so you have 4 bytes shown in binary and it is Little Indian. That means this is in GDB. Okay, that means we need to look from right to left. This is the most significant byte. You have a bunch of zeros, right? So I'm not writing all the zeros, 24 zeros, followed by 1, 0, 0, 1. That's basically the binary representation of this number. Okay. And now you can easily see that this is the place 2 power 7th place, and we are adding 1 to it. So it must be 2 power 7 plus 1. That's all. Consider the following fragment given below for a C function which takes integer types as parameters. What is the minimum number of possible integer input parameters to this function? So we don't know the function signature. Let's assume the function takes some integer inputs. We don't know exactly how many. We are trying to predict what could be the minimum number of possible integer types. So the way to reason about such questions is look at the binary and look at what is used with EBB. So you can see here it's EBB plus 8 and EBB plus C. C means 12. And EBB plus 4 is the return code, return address. EBB plus 8 is the first argument, plus C means the second argument. Okay, so that means there are only two places where EBB is referenced in a positive direction. So it's reasonable to assume there are two input parameters. So this would be my choice. Following assembly fragment, what is the return code status? So interesting question as well, because you see here we are basically calling exit of 5. The reason why I say exit is that the system call exit has the value 1 for EAX register and 5 must be for the input argument. Therefore, we are calling int is the interrupt. So exit of 5 is the answer. Okay, clear. And let's move on to the next one. Consider the following assembly statement. What is the value of EDX? So you can look at here very quickly and see whether EDX is changing anywhere. EDX is changing only here. That means 9 must be the answer. Okay. So this is the answer. All right. This is asking us to reverse engineer this little fragment and figure out whether the function returns a pointer. If a function returns a pointer, we should look at the EAX register and see whether EAX register has address. In this case, it doesn't seem like that because we update the place wherever EAX register is pointing to by a value 0. The EAX register itself is not an address, as we can see. It's not returning an address per se. Okay. So that's not the best choice. The function doesn't update the value of the first argument. Let's see whether the first argument is ever referenced. Okay, let's see. The first argument is referenced here because EBB plus 8 is the first argument. And the fact that we put a parenthesis here means that we are referencing the memory. That means the first argument must be an address. Okay. So the first argument, oh, here is one answer. The first argument is a pointer. And we are naturally updating that address with value 0.